So let's go back to the example that we've used before. The example of the length of time it takes to react to a stimulus given some percentage of a certain drug in the bloodstream. So let's assume that we have 5 observations from 1, 2, 3, 4, 5. So in total we have 5 observations. The value of x, so the percentage of certain drug in the bloodstream, is given in the second column, 1, 2, 3, 4, 5. And the length of time it takes to react to a stimulus is equal to 1 for the first observation, 1 for the second, 2 for the third, 2 for the fourth, and 4 for the fifth observation. When we sum the value of x, we get the value of 15. When we sum the value of y, we get the value of 10. And to calculate the mean value of x, we divide 15 by 5, so we get the value of 3. And to get the mean value of y, we divide 10 by 5, and we get the value of 2. Then in the next column, we calculate the difference between each value of x and its sample mean. So 1 minus 3 is negative 2, 2 minus 3 is negative 1, 3 minus 3 is 0, 4 minus 3 is 1, and 5 minus 3 is 2. In the next column, we calculate the difference between each value of y and its sample mean. So 1 minus 2 is negative 1, 1 minus 2 is negative 1, 2 minus 2 is 0, 2 minus 2 is 0, and 4 minus 2 is 2. And after this, we calculate the value of SS at xy, which is the product of these two differences. So negative 2 multiplied by negative 1 will be 2. Negative 1 by negative 1 is 1, 0 by 0 is 0, 1 by 0 is 0, and 2 by 2 is 4. So when we sum this, the values in this column, we get the value of 7. And then in the next column, we calculate the product of the difference between x and x with the bar, and x minus x with the bar. So in other words, we calculate the sum of squared differences between x and x with the bar. So negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So when we sum the values in this column, we get the value of 10. After this, we switch to the formulas, and so to get beta 1, we divide SS of xy, which we know from here is equal to 7, by the value of SS of xx, which we know from here is equal to 10. And we get 7 over 10, so 0.7. To get the value of beta 0, we take the mean value of y and subtract beta 1 multiplied by the mean value of x. So 2 minus 0.7 multiplied by 3 is negative 0.1. And in the end, we get the final regression model. So the estimated y is equal to negative 0.1 plus 0.7 multiplied by x. And we can give the following interpretation to beta 0. So when the percentage of a certain drug in the bloodstream is 0, so when x is 0, the reaction time y is equal to negative 0.1 seconds. And the question is, does it make sense? And I think you will agree with me that it doesn't, because I don't think the time can be negative. And beta 1 can be interpreted in the following way. So when the percentage of a certain drug in the bloodstream increases by 1 percentage point, the reaction time increases by 0.7 seconds. So when x increases by 1 percentage point or 1 unit, y changes by 0.7. So as you can see, 0.7 is nothing else but just the first order derivative of y with respect to x, and it shows the change in y given 1 unit change in x. We can also use the estimated model for the prediction and determination. So for example, let's predict the reaction time when x is equal to 2%. So we take the estimated model from here, and instead of x, we substitute the value of 2, and we get that if the percentage of drug in the bloodstream is 2%, the reaction time will be 1.3 seconds. And now, for example, let's determine the percentage of a drug in the bloodstream if the reaction time is found to be 2 seconds. So this time we know the value of y, we know the reaction time, it's 2 seconds, and what we are asked to find is the percentage of a drug, so the value of x. So we put 2 into the equation instead of y, x is the unknown. When we move negative 0.1 to the left, we get 2.1, and to get the value of x, we divide 2.1 by 0.7 and we get 3. So when the reaction time is 2 seconds, the percentage of a drug in the bloodstream is 3%.